Today we are going to discuss field effect transistor, that is called FET. The FETs are two types. One is JFET and MOSFET. JFET is junction field effect transistor. MOSFET is metal oxide semiconductor field effect transistors. JFET stands for junction field effect transistor. MOSFET stands for metal oxide semiconductor field effect transistors. So for our syllabus we have JFET. JFET, junction field effect transistor. The terminals are, what we have is source, drain, gate, and what we have the shield. Source, drain, gate, and we have the shield. In the junction field effect transistor, we consider one is construction part, another one is working part. So in the construction part, what we have is, we should have in one semiconductor bar. Now we have chosen N-type semiconductor bar. Then that is called N-channel FET. Then it is called N-channel FET. On the either side, we have the P-type semiconductors. Okay. For the N-type semiconductor, we dope P-type here. The terminals, one end is source, another end is drain, and another end is gate. The gate, both the P-type are connected together. That is what we declare as the terminal gate. The constructional part, let us have a one N-type semiconductor bar, dope the P-type semiconductor bar in the middle of that one. At that time, we call it as an N-channel FET. So this width, we call it as in channel. This width is what we declare as channel. This is called N-type FET. Now if we have the same part for the P channel, just you have this will replaced by P-type semiconductor bar and this one replaced by N. Okay. So P-type semiconductor bar, what we have is P-type semiconductor bar. On this middle one, we dope the N-type semiconductor bar. At that time, this becomes what is known as P-type FET. Usually we study that N-channel. So take it that N-channel, make it this P, this as P. So N-type semiconductor bar, on that one we had doped the P-type. The terminals are source, drain, gate. This is what we have the constructional part. So when we have the working part, we should connect the source for the source, drain, and to the gate. Now we are going to discuss FET, that is JFET, N-channel working. The terminal source, drain, gate we had connected. N-type semiconductor bar, on that one P-type semiconductor is doped. So this is heavily doped. N-type semiconductor bar is heavily doped and we have the N. Hence it is called N-channel FET. Hence it is called N-channel FET. Now we connect the source, okay, from which end N is negative. That N is what we declare as source. So we had connected here N. From this side it is forward biased. Here for the P-type we had connected the negative. At that time this becomes the reverse bias. Okay. For the P-type this is reverse bias. For the N-type here it is a forward bias. So you make VGS equals to 0. VGS equals to 0. At that time there will be no formation of depletion region. There will be no formation of depletion region in the channel. At that time the channel width will be larger. Channel width will be larger. So whatever the majority charge carriers emitted from the source, whatever the charges emitted from the source will comes to the drain. That forms what is known as drain current. That is called as a drain current. Okay. So whatever the majority charge carriers emitted from the source, it gets into the drain. So at that one, what we declare as drain current. So this part, the channel width is larger. So when we draw the graph, VDS versus ID. So as you vary the VDS, ID will increases. As you vary the VDS, ID increases. And this part we divide into ohmic region, pinch off region and the breakdown region. So the channel width is larger, at that time the drain current will be larger. So for VGS equals to 0 volts, slightly you increase this voltage, VGS equals to minus 0.5. So at that time what has happened, there will be a formation of depletion region due to the reverse bias, because negative is connected for the P region. At that time the channel width will decrease. On both the sides there will be a formation of depletion region. There will be a formation of depletion region. At that time the channel width decreases. Once the channel width decreases, what will happen? Whatever the voltage you vary this VDS from the source to the drain, the majority charge carriers flowing from this end to this end slightly decreases because of the channel width increased. Okay, at that time depletion region increased. So as the channel width decreased, what has happened? The drain current decreases. Now we will increase VGS, gate to the source voltage, is equals to minus 1 volts. VGS equals to minus volts. At that time what is happening here? This part, the depletion region increases. When the depletion region increases, what happened? The channel width decreased. The channel width decreases. So at that time when you vary this VDS, the majority charge carriers from source to drain flowing will decrease. The drain current decreases. That is, you are pinching the semiconductor bar by applying the VGS. You are pinching the semiconductor bar by applying the VGS volts. Okay. So as you increase the reverse bias, there will be a formation of depletion region, right? As the depletion region increases, the majority charge carriers flowing from source to drain will decrease. Okay. So at that time drain current goes on decreases. So VGS equals to minus 1 volts. Minus 1 volts. So once more I will recall, for the N channel FET, we would take in N type semiconductor bar having the source, drain, gate, the terminals. Connect the VDS source, that is N to negative, that is source. D will become connected to the positive of the terminal. The terminals will become as VDS. For the gate, you connect the negative, that is for the P. Negative if you are connected, then it is reverse bias. So positive you connect to the source. At that time this becomes what is known as a reverse bias. So this part is forward bias and this part is reverse bias. Now if you apply the voltage to the VDS, all the majority charge carriers from the source to the drain flowing, that is N channel is electrons. When the channel width is 0 or channel width is very large, when VDS equals to 0, VGS equals to 0, the channel width will be wider. There will be a more drain current, that is you have the drain current will be larger. When VGS is minus 0.5, the depletion region increases, slightly increases, the channel width decreases. At that time, what's happening? The drain current will decrease. So this is the second graph. So when the VGS is minus 1 volts, at that time again the depletion region increases due to the reverse bias. At that time again the channel width decreases. So at that time drain current decreases. It goes on. That means we are pinching the semiconductor bar by applying the VGS volts. By applying the VGS volts. Now we will study the characteristics of the FET. Now we are going to discuss the characteristics of field effect transistors. One is the drain current characteristics, another one is mutual characteristics. One is the drain current characteristics is ID versus VDS. Mutual characteristics is ID versus VGS. So when VGS equals to 0 volts, the drain current increases and becomes active region, and this becomes the breakdown region. Here rapidly increase, as the voltage increases, current increases up to this part. Here it is in the active region or pinch off region, and this is breakdown region. Here as voltage increases, current increases. This part we call it as an ohmic region. This part is declared as ohmic region, and this part is what we declare as active or pinch off. Active or pinch off. This one is breakdown. So the FET should be operated within this range. Here means both the junction of the depletion region will touch each other and the device will goes off. So within this limit we should be operate. That is why the curve here we declare into the three parts. One is ohmic region, another one is active region or pinch off region, another one is breakdown region. In the case of a mutual characteristics is ID versus VGS. Here in this case what's happened, see here, as VGS is 0, drain current is maximum. That drain current what we declare as IDSS. ID, that is drain current at saturation. So drain current is maximum when VGS equals to 0. As the VGS is increased, what happened? As VGS is increased, the drain current decreases, because there will be a formation of depletion region inside the junction. At that time what will happen? The drain current decreases. As VGS increases, drain current decreases. Now we will take a slope on the ohmic region. At that time, if we take a slope on the ohmic region and a slope on mutual characteristics. Here the small portion is what we declare as delta VDS and delta IDS. Delta ID, delta VDS. So drain resistance RD is equals to delta VDS by delta ID. So voltage by current is nothing but an resistance. Voltage by current is nothing but an resistance, that is RD is equals to delta VDS by delta ID. At the same case, take the slope of this one, that is what we declare as GM, that is called transconductance delta ID by VGS. Delta ID by delta VGS. That is what we have is the transconductance of the field effect transistors. So, one is drain resistance delta VDS by delta ID, and GM is transconductance delta ID by VGS. Transconductance is nothing but an just opposite of resistance. Resistance is what? Voltage by current. Conductance is what we declare as current by voltage. In the FET we treat that as GM, that is called transconductance. So, mu, the new factor, that is called amplification factor, mu is equals to GM into RD. Mu is called amplification factor. That means what we have is GM is delta ID by delta VGS into delta VDS by delta ID. So, this delta ID will get cancels, that is delta VDS delta VGS. This is what we have the amplification factor, that is called mu. So, one is the drain resistance. Drain resistance RD, GM is the transconductance, whereas this mu is another part, that is what we declare as amplification factor. Amplification factor. So, once more I will recall what we have the FET characteristics. Here we have the drain characteristics and the mutual characteristics. So, here ID on the y axis, VDS on the x axis, VGS on the fourth quadrant. Okay. Now, ID and the VDS, this gives you drain characteristics, that is called output characteristics. First, when VGS equals to 0, maximum drain current, that is IDSS. So, this curve we divide into three parts. One is ohmic region, active region, breakdown region. Active is also called pinch off. Ohmic, active, breakdown. Ohmic, active, breakdown. Okay. Now, the mutual characteristics is what we have is as ID is maximum, as VGS is increased, it goes on decreases. At that time it comes to almost 0. So, draw the slope on the ohmic region. At that time we get is what is known as an drain resistance. What we have this drain resistance, that is delta VDS by delta ID, delta VDS by delta ID. GM is what we have from the drain mutual characteristics. You take the slope, that is delta ID by delta VGS, that is called transconductance. So, here delta ID delta VGS, delta ID by delta VGS, that is called transconductance. The new factor, what is known as the amplification factor, mu is equals to GM into RD. At that time mu is equals to delta VDS by delta VGS, that gives you amplification factor. The Shockley equation for drain current is given by ID, that is the drain current, is equals to IDSS, that is drain current at saturation, that is the maximum, 1 minus gate source voltage VGS divided by peak voltage to this whole square. This will get you the 1 marks question. Write the Shockley's equation for drain current. ID equals to IDS is 1 minus VGS by VP. Now we will consider the FET and BJT. So FET is what we have is field effect transistor. Another one is BJT, that is bipolar junction transistor. So in the FET, what are the terminals? Source, drain, gate. Whereas in the case of in PNP or NPN transistors, what we have is for the source equivalent is emitter. Here majority charge carriers will take part in the conduction process. Here also in the case of an BJT, emitter which emits the majority charge carriers. Drain, that is it is collects, that is here we call it as an collector. Here source, here it is emitter. Here drain, we call it as an collector in the BJT. Here we have the gate. So here what we have is that is called base. Emitter, base, collector is used in the BJT, NPN and PNP transistors. NPN and PNP transistors. In the case of an FET, either N channel or P channel, we call it as a source drain gate. So source drain gate. Source is represented by S, drain is D, gate is G. So SD, G. So this is the comparison between field effect transistor and the bipolar junction transistors. One more thing is what we have is it is a voltage control device, that is we are applying the VGS. When the VGS is applied, what will happen? The semiconductor bar, there will be a formation of depletion region. As such, the drain current decreases. Here base, what will happen? Here base current, it is current controlled device. Here current controlled device. As the base current increases, the collector current increases. Hence what we have is this is a voltage controlled device, this is called current controlled device. Now base control, once more I will tell you, this is the comparison of the FET and BJT. What is source, drain, gate, that is the terminals of FET, and this is a voltage control device. In the case of an bipolar junction transistor, emitter, collector, base, and it is a current controlled device. Now what we have the circuit symbol of N channel and P channel FET. Now we have this. This is the circuit symbol of FET. Now this one end we called as in source and this end we call it as in drain, and this is called gate. Source, drain, gate. If the arrow mark pointing inwards, we call it as an N channel. This is called N channel. At the same case, if we have the P channel, pointing outwards, at that time see the only difference is with respect to this arrow mark. Yeah, this is source, drain, gate. This is called N channel. Automatically this becomes P channel FET. P channel FET. So here once more I will tell you, source, drain, gate. This arrow mark represents pointing towards inwards, means it is N channel. If the pointing towards outward, we call it as an P channel FET. So as the same case, if you consider the bipolar junction transistor, emitter, base, collector. So this is what we have is pointing towards outward. At that time, NPN transistors. So if you have this PNP transistor, emitter, base, collector. See here, this is PNP transistors. So the symbol, listen carefully, if it is arrow mark, that represents the emitter in this case, pointing towards outward, then it is called NPN. If the arrow mark pointing inwards, then it is called NPN transistors. So emitter, base, collector. Here emitter, base, collector. This is what we have the BJT. This is FET. So source, drain, gate, source, drain, gate, N channel, P channel. Now we are going to discuss the formulas which are coming under the FET. One is drain resistance RD, that is VDS ID. It is the ratio of drain source voltage to the drain current. And another one is transconductance GM. It is ID versus VGS. Drain current, it is the ratio of drain current to the VGS. It is a small proportion, for that reason we take the delta. And the important one is the amplification factor mu is equals to GM into RD. That is, it's a product of transconductance and the drain resistance. The Shockley equation is ID equals to IDS is 1 minus VGS by VP whole square. That is Shockley equation for the drain current characteristics. So drain resistance, transconductance, mu is equals to GM into RD. For this one, the unit SI unit is ohms. For this one, unit is mhos or Siemens. Any one we can call it. Here no unit, it is a constant. For this one, it does not have any unit. So drain resistance, it is in resistance ohms. Transconductance, it is mhos or Siemens, or else we can also write MHOS, mhos. Here mu is equal to GM into RD, that is resistance and mhos will get cancelled. At that time it is a constant. So ID is equal to IDS is 1 minus VGS VP. This is amps. In the FET, what we have is one 3 marks question for the description. That is either working of an FET or construction of FET or characteristics of an FET, etc. These are the most likely questions. In the 1 marks question will be what we have to calculate the transconductance or to calculate the drain resistance or to calculate the amplification factor or to calculate the IDS, that is the saturation current ID. So these are all the different terms what will occur in the FET. So write the symbol of N channel FET. N channel FET. Second one, compare FET with respect to BJT. Write the symbol of N channel FET, compare FET with respect to BJT. Thank you dear students, we shall meet in the next class.